Hi everybody, this is my first video going through some Edexcel papers, so I'm going to start with A-Level Maths Pure 1 from October 2020. This question is to do with the binomial theorem. So we've got 1 plus 8x to the power of a half, and we need to expand that to the first four terms. Well, we know that from the binomial theorem that if we've got 1 plus x to the power of n, then that can be expanded as 1 plus n times x plus n minus 1 x squared over 2 factorial, and then it's another n minus 1 n minus 2 in another factor in the numerator, increase the power of the factorial, increase the power of x, and so on. Okay, so for this one we've got 1 plus a half, and then our x value is 8x here, so the second term in the binomial, so we get that, and then plus half minus 1, which is minus a half, times 8x all squared divided by 2 factorial, and then a half minus a half minus 3 halves, then 8x cubed this time, and then divided by 3 factorial, and that's where we need to go. That's 4 terms, so we stop there. So it's just a case of simplifying then. So we've got 1 plus a half of 8 is 4. A half times minus a half is minus a quarter. 8 squared is 64. So minus a quarter times 64 is minus 8. Sorry, minus 16, and then divided by 2 is minus 8. So minus 8x squared. And then the last one, a half times minus a half times minus 3 halves, that's 3/8 divided by 3 factorial, and then multiplied by, so divided by, so we've got 3 over 8 times 8 cubed over 6. And if we put all that together, we get 32, so 32x cubed. Explain how you could use x equals 1 over 32 to find an approximation for root 5. Well, first of all, we've got a power of a half. So 1 plus 8x to the power of a half, that's the same as the square root of 1 plus 8x. So there's where the square root comes in. And if we just substitute that value in, so if we sub in x equals 1 over 32, we get 1 plus 8 over 32, which is a quarter. So we get root 1.25. So how can we use that to find an approximation for root 5? Well, root 5 is 4 times 1.25. So that's root 4 times root 1.25. And root 4 is just 2. So in other words, so we should sub in 1 over 32 into the expansion, and then just double the answer that we get. And that will give us an approximation for root 5. Question 2. We just want to solve this log equation. Find p to 1 decimal place. So we can choose whatever logs we want. So 4 or 5 might be a more sensible choice, but I'll just use natural logs. So 3p minus 1 times ln 4 is equal to 210 ln 5. So what I've exploited here, for example, is that one of the laws of logarithms allows me to take the power to the front as a coefficient. So I've just applied that to both sides. Then I need to multiply this out and isolate the p terms. So I've got 3p ln 4, then I've got minus ln 4, which I'll put on the other side. So plus ln 4. And therefore p is equal to, if I divide by 3 ln 4, I get p. And I want an answer to 1 decimal place, so if I put that into my calculator, I should find 81.6 is the answer. Okay, question 3. is to do with vectors. So we've got position vectors of 3 points A, B, and C, and we want to first of all find the vector AB. Well, we know that that's going to be equal to, let's just draw a little diagram. So here's the origin. That's what the position vector is measured relative to. Here's A, and here's B. So if I want to find AB, then I can do that by going A to O, then O to B. Okay, so AB is minus OA, then plus OB. But minus OA is, so that's just minus the position vector. So that's minus 2i plus 5j minus 6k, then plus B, which is 3i minus 3j minus 4k. And 3i minus 2i is I, minus 5j minus another 3j, that's minus 8j, and then minus 6k is 6k, and then minus another 4k, that gives minus 2k. Okay, so there's AB. Show that quadrilateral OABC is a trapezium given reasons for your answer. Well, what we can see is that O to C is exactly twice A to B. Okay, so therefore OC and AB, let's write this, so OC and AB are parallel, and if you've got a four-sided shape, OABC, and two sides are parallel, that's the definition of a trapezium. Okay, now we didn't need to check any other sides, because if say OA and OA and BC were parallel as well, that would give a parallelogram, but a parallelogram is just a special case of a trapezium. So it suffices just to do that. Question 4 now is about functions, and we're given a function and we're asked to find its inverse first of all and evaluate that at a certain point. So the easiest way to deal with inverses is just to rewrite this in terms of y, and then we rearrange this to make x the subject. So the first thing we do is multiply across the x minus 2 from the right hand side, multiply everything out, collect terms in x on the left hand side and move all the other terms to the right. And then if we factorize on the left hand side, then we can divide that across. Now what we also know is that a function and its inverse are mirror images of each other in the line y equals x. So if this was f of x, then f of minus x would look like that. Yes, f of minus 1 of x, the inverse. And this line here is y equals x. So what we do in the last step then, because of this idea, is that we swap labels y with x. So y becomes equal to 2x minus 7 over x minus 3. And we want to evaluate this at x equals 7. So inverse function at 7 is 2 times 7 minus 7 over 7 minus 3. So 14 minus 7 on top, that's 7 on top, and divided by 4 on the bottom. So 7 over 4 is the answer. Part B, show that f of x is ax plus b over x minus 3. Okay, so to compose f and f together, we have to substitute one f of x in place of the x's in the original function. So f of x is equal to 3. And then instead of x, we put 3x minus 7 over x minus 2, and minus 7. And in the denominator, instead of x, again, we substitute f of x. So we get that. If we multiply top and bottom by x minus 2, we get 3x minus 7 minus 7x minus 2 divided by 3x minus 7 minus 7x minus 2. And if we then just simplify that, we got on the numerator, we've got 3 times 3x, that's 9x, minus 7x, so that's 2x. And 3 times minus 7 is minus 21, plus 14 is minus 7. And then dividing by, well, simplifies to x minus 3 on the bottom as well. Question 5. Okay, so we're told the car has 6 forward gears, first to 6th gear, and the fastest speed in each gear is given there. So first of all, we're told that the fastest speeds in each gear is an arithmetic sequence. So in an arithmetic sequence, the nth term is the first term plus n minus 1 times the common difference d. So we just, in this sort of question, we just write down what we know. So we can say that u1 is equal to, well, 1 minus 1 is 0, so u1 is just the first term, and that's equal to 28. And we know that u6 is going to be equal to, well, we already know what a is, 28, so we can say 28 plus n minus 1, so that's 5 times d. And that's equal to 115. So if we take the difference of those, we get 5d is equal to 87. So d is 87 over 5. So then find the fastest speed of the car in 3rd gear. So u3 is the first term, 28, plus n minus 1, so that's 3 minus 1 is 2, multiplied by d, which was 87 over 5. And if you put all that together, you get 314 over 5 kilometers per hour. Okay, B is similar, except that this time the speeds form a geometric sequence. So again, just write down what we can. Well, just like before, we get u1 is equal to a, which is 28. That makes things easier. And u6 is a, which is 28, times r to the power of n minus 1. So that's 5. Okay, so I'll just write that down. So that's what we know for a geometric sequence. And that's equal to 115. So r to the 5 then is 115 over 28. So r is the 5th root of 115 over 28. And then we want to actually find u5. So we've got 28, so that's a times 5th root of 115 over 28 to the power of 4, n minus 1, 4. And if you put all that together, you get about 86.7 kilometers per hour. Question 6. Express sine x plus 2 cos x in the form r sine x plus alpha. And we want to find the exact value of r and alpha to 3 decimal places. So we use the compound angle formula here. So r sine x plus alpha, it can be written as r sine x cos alpha plus r sine alpha cos x. And then if we compare that to what we're trying to rewrite, so that's sine x plus 2 cos x, and we just compare terms that involve sine x on both sides and that involve cos x on both sides. So if we compare the sine x terms, we get 1 equals r cos alpha. And if we compare the cosine terms, we get 2 is equal to r sine alpha. Okay, now to find r, we square and add these. So we get 1 squared plus 2 squared. So what we're doing is we're squaring both sides and adding them, and we're using the fact that sine squared plus cos squared equals 1. Okay, the Pythagorean identity. So we get r squared equals 5, so r is equal to root 5, and that's, as asked for, that's exact. To find alpha, we divide one by the other. So if we divide the sine one by the cosine one, so r sine alpha over r cos alpha, that's going to be 2 over 1. And if we simplify that, we get tan alpha equals 2, so alpha is equal to inverse tangent of 2, which to 3 decimal places is 1.107. Okay, then we're told that the temperature inside a room is given by this quite large equation. And first of all, we want to deduce the maximum temperature of the room during the day. Well, first of all, let's just rewrite this using our previous result. So instead of 5 plus sine blah 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 plus 2 cos, all that, we'll just write that theta is now equal to 5 plus root 5 sine, then it was x plus alpha, so x plus 1.107. So if we want to deduce the maximum temperature, well, the maximum of this function will be when the sine part is equal to 1. Remember, sine has a maximum value of 1. So when the sine part is equal to 1, theta is just equal to theta is equal to 5 plus root 5. So that's the maximum temperature. And then the last part, find the time of day when the maximum temperature occurs. Well, same sort of idea. The maximum temperature is when the sine part is equal to 1. So when is sine equal to 1? The sine is equal to 1 when the angle is equal to pi over 2. So the argument of the function is pi over 2. So what's the argument? Well, this x in here is the pi t over 12 minus 3. So what we've got is that pi t over 12 minus 3 plus 1.107 is equal to pi over 2. Okay, for the first maximum of the day. So if we rearrange that, we get t is equal to pi over 2 plus 3 minus 1.107, and then multiplied by 12 and divided by pi. Okay, so that's just rearranging all in one step there. And if we do that, we get an answer of 13.23. Now, the question says give the answer to the nearest minute, so we can't have a decimal fraction of an hour. So what we need to do is just convert that into minutes. So we take the 0.23 bit and we multiply it by 60, and that gives approximately 14. So the answer is 13 hours and 14 minutes. Question 7. We've got a region R which is bounded between a straight line and a quadratic. and we're told some information about the line in the quadratic. First of all, both the line and the quadratic cross at y equals 25. They also intersect at -2 and 13, which is also the turning point of the function. So what we can do, let's start off with the line, since lines are always simpler than quadratics. So the line itself, we know that general equation of line is mx, y equals mx plus c, but we can immediately put in the 25 because c is the y-intercept. And we can work out the gradient of that line. So delta y over delta x, so 25 minus 13. Okay, so we're taking the 2 points 0 and 25 minus 2 and 13 divided by the x values, so 0 minus 2. So that gives 12 over 2, which is 6. So the equation of the line is y is equal to 6x plus 25. The equation of the quadratic, okay, if it has a minimum point at -2 and 13, then using our knowledge of completing the square, we can write down that the equation must be, we know that usually it's the other way around, usually we complete the square and then deduce something about the turning point. So we're doing it sort of backwards here from what's normally done. So if the minimum point is x minus 2, then the term inside the square must be x plus 2 squared. Okay, so that is obviously a minimum when x is minus 2 because that term becomes 0. And when that is equal to 0, y is equal to 13. So that's a equation for the quadratic. But however, this term, the square term, could be 0 if x is minus 2, but also if anything is multiplied outside. So we'll put in a general coefficient a outside as well. Now if we use the other point that the quadratic passes through, which is 0 and 25, we substitute that in there, we get 25 is equal to 4a plus 13, and that allows us to find that a is equal to 12 over 4, which is 3. So the quadratic has the equation 3x plus 2 squared plus 13. And so the question asks us to define R. Well, R is beneath the straight line and above the quadratic. So we can say that for R, we've got the y values are less than the quadratic line, but greater than the less than the straight line, but greater than the quadratic line. Right, question 8. So this is a question all about coming up with a differential equation from a word problem. So a smartphone is released, a company monitors the total number of phones sold, and they call that N, T days after the phone was released. They observe that the rate of increase of N was proportional to N. So the rate of increase, well, rate means with respect to time. And we want the increase of N, so that's dN by dt, is proportional to N. Now, because it's an increase, I'll just leave it like that. If it was decrease, I would have said maybe proportional to minus N. But what we'll do now is we'll just remove that proportionality constant and we'll write it like that. So dN by dt is equal to k times N. And we need to find an equation for that, so we just got to solve this. And this is an example of a separable equation. So what we do is we move all the n's to one side. So divide the n across, we leave the k where it is and multiply the dt across. Okay, and then integrate. So 1 over n is the logarithm of n. and k is just a constant, so if we integrate that we get k times t and then plus our constant of integration. To get rid of the logarithm we need to exponentiate both sides, so we get n is equal to e to the kt plus c. And we know from rules of logarithms that if we have a base and then we have a sum of powers, we can split that up into akt times e to the c. And then what's usually done is that this is relabeled. So let's say that ec is equal to a. So we can say that n is equal to a e to the power of kt. Question 9. We've got this curve f of x. Okay, I'll write it a bit larger. Okay, so that's the equation of the function, and we first of all want to find f of f primed, the derivative of this function. Okay, so how do we do that? Well, just use the product rule. So we'll differentiate the bracket first. So we got x squared differentiates to 2x and leave the exponential alone, and then we'll differentiate the exponential part and use the chain rule to do that, and leave the bracket alone. And the 4 I've just put in front of both terms because that's just a constant. Nothing happens with that. If we collect terms, well, what we can see first of all is that we have a 4 and a 2 here, a 4 and a 2 there, that multiply everything. So I can take out a factor of 8. I can also take out the exponential as a factor from both terms. And then what am I left with? Well, from the first term I've got x, and from the other term, remembering that I've already taken out the 4 and the 2, I've got minus x squared, so x squared times minus in there, and then I've got minus 2 times minus 1, which is plus 2. And that's basically what we're asked to find, just in a slightly different order. Okay, so that's part A. Part B, hence find in the simplest form the exact coordinates of the stationary points of C. So if we want to find stationary points, we're just saying f primed is 0. And we know that the exponential part can never be 0. So we've got x minus x squared plus 2 equals 0. And let's write that in terms of, let's multiply through by minus 1 and reorder it. So x squared minus x minus 2 is 0. And we can see then that that factorizes. And that factorizes as x minus 2 and x plus 1. So x is equal to 2 or x is equal to minus 1. And we want the coordinates, so not just the x values, but the y values as well. So we need to substitute these back into f of x. So we get y is equal to, well, for the first one, if x is equal to 2, we're going to get 4 times 2 squared minus 2, which is 4 minus 2 is 2, times e to the minus 4. So that's 8 e to the minus 4. And for the other one, if we substitute in minus 1, we get 4 times 1 minus 2, which is minus 1, and then times e squared. So we get minus 4e squared. So x equals 2, y equals 8e to the minus 4, and x equals minus 1, y equals minus 4e squared. Okay, the last part defines two other functions. So these are just transformations of the function. So first of all, g of x. G of x is just 2f of x. So what we can say, first of all, is that the range of g is just going to be twice the range of h. So let's find the range of h. Well, we know that from our diagram, this point here, this turning point must be minus 1 and minus 4e squared. So so the range of h originally was from the lowest point of minus 4e squared and then, well, just greater than or equal to that. So the range of h, the range of g, sorry, is greater than or equal to 2 times minus 4e squared. Okay, so greater than or equal to minus 8e squared. Okay, and there's no upper limit on that one because the domain of g is also x for all real values, so it goes up to infinity as x becomes negative. That's part I. Now II. So h is twice the function and then minus 3, but also we're told that x is greater than or equal to 0. So what we need to find out is what's the value when x is equal to 0. So when x is 0, f of x, let's do f of x first, was 4 times minus 2 times e to the 0, which is 1. So that's just minus 8. And what we'll need this time is we do have a maximum point because for positive values of x, the maximum value of f was this point here, which was, remember, x equals 2 and y equals 8e to the minus 4. So for x greater than or equal to 0, f of x was between minus 8 and 8e to the minus 4. So therefore 2f of x minus 3. Okay, so if we just double and subtract 3 from both sides, that's going to be greater than or equal to minus 8 times 2 is minus 16. So minus 8 times 2 minus 3, so that's minus 19. And at the other side we've got 8e to the minus 4 times 2 minus 3, so that's 16e to the minus 4 minus 3. So they're the limits on h. Okay, so that's the range of h. Question 10. So we're asked to use a substitution first of all to show that this integral can be rewritten more simply. So whenever we use a substitution, what we need to remember is that we need to change the variable of integration, and we do that by differentiating the substitution. So dx by du is going to be 2u. What we'll also need is we'll need to rearrange the substitution for u. So we will get that u is equal to, well, first of all, u squared must be x minus 1. So u is root x minus 1. Okay, so we might need all of that. Let's just rewrite the first one as dx is equal to 2u du as well. Okay, so we're going to substitute all of that in. Other thing that we've got is we've got limits here. So we'll need to change those as well. So we'll use this. So u is equal to root x minus 1. So when x is equal to 10, u is equal to root of 10 minus 1, which is 3, root of 9. And when x is equal to 5, u is equal to the root of 5 minus 1, so root 4, which is 2. So p is 2 and q is 3. They're the new limits. So we're just going to put everything together now. So new limits, put those in. So dx on the top we're replacing with 2u du. on the bottom I've got an x minus 1. Well, I know that that's equal to u squared. And then I've got 3 plus 2 times root x minus 1, so that's 3 plus 2u. And then all I need to do then is cancel it 1u from the numerator with one of these from the denominator. And then 3 times 2 is 6, so I've got 3 to 2 of 6 du divided by u times 3 plus 2u, which is what I was after. Okay, so hence using algebraic integration, show that we can write the value of that integral is just the logarithm of some constant. Okay, so what we can do is we can say that's 6. So 6 over u, 3 plus 2u, we can split this up into partial fractions. So we've got a over u plus b over 3 plus 2u. And that leads us to be able to write down, if we cross multiply, that a 3 plus 2u plus b times u is equal to 6. Yeah, it's equal to 6. So what we do here to find a and b is we just always choose suitable values of u. So if I put u equals 0 in, first of all, that eliminates the term that has a b in, and I'm just left with 3a equals 6. So therefore a is 2. And if I use u equals minus 3 over 2, that will eliminate the first term, and I'll just be left with minus 3 over 2b is equal to 6. So b is equal to 2 times 6 is 12, divided by minus 3, that's minus 4. So therefore I can write the integral as 2 to 3 of a over u, so that's 2 over u, plus b over 3 plus 2u, so that's minus 4 over 3 plus 2u. And we can do those integrals now. So we get 2 over u, well that's just 2 times log u. Usually we'd put modulus bars around the u as well, but the limits here are both positive, so it doesn't really make a difference here. And then minus 4 times logarithm of 3 plus 2u. And then because of the reverse chain rule, we need to also divide by the derivative of the inner function. So dividing by 2 there. And then integrating that from 2 to 3. So we get, and obviously we can just simplify that a little bit more. 4 over 2 is 2. So 2 log 3 minus 2 log 3 plus 6, 9. So we get that from the upper limit, and then minus 2 log 2 minus 2 log 3 plus 4 is 7. So we get that. We could take a factor of 2, or we could just put all the powers inside as the coefficients inside as powers. So 2 log 3 is log of 3 squared, which is 9. 9 squared is 81. 2 squared is 4. And then remember I've got minus minus, so that's plus. And then 7 squared is 49. So we can write that using rules of logarithms again as if we add logs together, we multiply, so 9 times 49. And if we subtract logs, we divide, so 81 times 4 on the bottom. And that simplifies. So 9 over 81 is 1 over 9. So we've got 9 on the bottom. 9 times 4 is 36, so 49 over 36. Right. So we've got some circles to deal with now. So we're given the equations of both the circles, x squared plus y squared equals 100 for circle 1. So that's centered on the origin and has a radius of 10. The other one has a radius of root 40 and is centered at x equals 15, y equals 0. And we're told that the circles intersect at the points A and B. So show that angle AOB is 0.635 radians. So first of all, what would be useful to do is just find the coordinates of A and B, because we'd like to find the distance between A and B to be able to draw a triangle and work out the angle. So what we need to do is we need to solve the circle equations together. So x squared plus y squared is 100, and x minus 15 squared plus y squared equals 40. So if we subtract one from the other, we're going to get x squared minus x minus 15 squared. The y squareds obviously cancel, and then 100 minus 40 is 60. If we multiply that out, the x squared terms will cancel, and we're going to get inside that bracket minus 30x, and we've got a minus in front, so that's 30x. And then minus 15 all squared is 225, so minus 225 equals 60. So 30x is equal to 285. So x is equal to 285 over 30, and that simplifies to 19 over 2. So the x value here, where these meet, is 19 over 2. So if we substitute that back into the first equation, we get that y is equal to plus or minus the square root of 100 minus x squared. So plus or minus 100 minus 19 over 2 squared, and that gives plus or minus root 39 over 2. So root 39 over 2 is A, minus root 39 over 2 is point B. So let's just split this angle, do this in half, so we can say that angle theta there. So I've got so this side here is root 39 over 2 from the x-axis up to A, and what we also know is that the distance along the adjacent side is just the value of x, so that's 19 over 2. So we can say that tan theta is opposite over adjacent, so the 2's cancel, so we've got root 39 over 19, so theta is equal to, if I do inverse tangent, 0.3176. So therefore angle AOB is twice that, because we split it in half. So to three significant figures, that's 0.635 radians. Okay, which is what we're after. Part B, the region shown in figure 3 is bounded by C1 and C2. Find the perimeter of the region. Okay, so let's just rule off that. Okay, so the perimeter of the whole shape, so the distance around the edge, what we're just going to have here is we're going to have these two bits added together. So it's just two major arcs of the circle. And to find a major arc, we're going to do 2 pi minus the angle subtended. Okay, so we're going to have to find this point as well. So let's call this D. So we need to find angle ADB, so we can find the arcs that are missing. So first of all, let's find arc A to B for circle 1. Okay, so remember the equation is r theta. So the radius of circle 1 is 10. Then we can just get that straight away from the equation. And the angle subtended, we just worked that out in the first part, 0.635. So the arc length A to B, sorry, I should say that's the minor arc, is 6.35. And therefore the major arc, I should just work that out straight away, is 10 times the bigger angle, so 2 pi minus 0.635. And that gives 56.5. So this is 56.5 all the way around there. So we need to do the same for C2. So we'll do the same sort of thing as before. I'll just change colour so it's a bit less confusing. So we've got point D here, and then this is A. So I need to find this angle here. I'll call that alpha. So again, this side of the triangle is 39/12, just as before. But this distance along the adjacent side, well, D is the centre of the circle 2, so that's 15. And the value at the other side was 19/2. So this distance here must be 15 minus 19/2. Okay, I'll just write those bits on. So these were the x values at those points. So we can say that alpha is equal to, if we work that out same way as before, so inverse tangent of root 39 over 2 divided by 15 minus 19/2. And we find that the angle is about 0.516. So we find that ADB, which is what we're actually interested in, is about double that, and it turns out to be 1.033. So the major arc for C2 is going to be equal to 10 times 2 pi minus 1.033, which is about 33.2. And therefore the total perimeter is just the sum of those two arcs. So 56.5 plus 33.2, and that gives 89.7. Whew, that was quite a long question. Right, 12. In this question, you must show all stages of your working. Right, okay, so we've got to just solve this prove this trigonometric identity. So cosec theta minus sine theta. Whenever we're solving identities, always start from the side that looks more complicated. So you've got a sum of different things that's complicated. So we'll start there, and we'll write cosec as 1 over sine. So we get 1 over sine minus, and then sine theta, well, I'll write sine theta as sine theta over sine squared theta over sine. And the reason for doing that is so I've got a common denominator. So I can then write that as 1 minus sine squared theta over sine. 1 minus sine squared is cos squared, of course. And then I'll split that up into, so cos squared is cos times cos, so that's cos theta times cos theta over sine. And cos over sine is cot. So there we are. Part B, hence or otherwise, solve that. So what we can say then is that if we use the identity in there, we can say that cos x times cot x is equal to cos x cot 3x minus 50 degrees. So first of all, one solution to that is if cos x is equal to 0. And if cos x is equal to 0 in the interval that we're solving in is 0 to 180, then that leads to x equals 90 degrees. Okay, so cos, just remind ourselves, cos theta looks like that. So between 0 and 180, the only solution is there, a 90. Okay, or alternatively, the cotangent bits are equal. So that would mean that x is equal to 3x minus 50. And if we solve that, move the x's across, we get minus 2x is equal to minus 50. So x is equal to 25 degrees. So there's another solution. But we also know that cotangent, 1 over tangent, has a period of 180 degrees. So an alternative is that instead of just x is equal to 3x minus 50, we could have said x plus 180 degrees is equal to 3x minus 50 degrees. And if we solve that one, same way, so minus 2x there, take the 180 to the right to make minus 230, so x is 115 degrees, is actually a third solution. So we've got 3 different solutions here. X equals 90, x equals 25 degrees, and x equals 115 degrees. Okay, so don't forget about the periodicity of these functions, because there might be extra ones that you haven't considered. Right, sequences next. So we're given a recurrence relation, a n plus 1, so the n plus 1th term is related to the nth term as shown. And we're also told that the first term, a1, is equal to 2, and that the sequence has is periodic of order 3. Okay, so what that means, periodic of order 3, it means that the 4th term will be equal to the first term. So it repeats every 3 terms. So it goes around in a cycle. And we want to show that, first of all, that quadratic's 2. Well, what can we do? Well, first of all, let's just try and work out the terms then. So a1, we're told, is equal to 2. So a2 must be equal to, and we just substitute these into the formula. So we're going to get k times 2 plus 2 over 2, which is 2k. So a3 is equal to k times 2k plus 2 over 2k. So k cancels there and there, and then the 2 will cancel, so we'll just be left with k plus 1. And then a4 is going to be k times k plus 1 plus 2 over k plus 1. So we get k times k plus 3 over k plus 1. That's about as much as we can simplify that. But we know that it's a periodic sequence of order 3, so we know that this 4th term is equal to the first term. So we can say that k plus 3 over k plus 1 is equal to 2. And then we just got to rearrange this to get what's shown. So k plus 3 is equal to 2k plus 1. So k squared plus 3k equals 2k plus 2. And if we just move everything to the left hand side, we get k squared plus k minus 2 equals 0. Part B, for this sequence, explain why k cannot be equal to 1. Okay, so if k was equal to 1, then what we would have is we'd have a1 is equal to 2. Well, that didn't depend on k. We'd have a2 is equal to 2. We'd have a3 is equal to 2. We'd have a4 is equal to 2. So what we'd actually find is that every term would be the same. Okay, which is a sequence. Okay, there's no problem with that. But the problem is that this is not periodic order 3. In fact, this is periodic order 1. Every term is immediately the same as the previous one. And then last bit is find the value of this sum. So r equals 1 to 80 of a to the r. Well, let's go back to this quadratic. So k squared plus k minus 2 equals 0. So the solutions were these. K k plus 2 and k minus 1. So k is equal to minus 2 or minus 1 equal to 1, and we've just discarded that one. So we've got k equals minus 2. So the first few terms are a1 is equal to 2, a2 is equal to 2 times minus 2, which is minus 4, a3 is equal to minus 2 plus 1, which is minus 1, and then we're back to 2 again. Okay, and so on. So what we find is that every 3 terms, okay, and we're starting at r equals 1, every 3 terms, the sum is 2 plus minus 4 plus minus 1, which is minus 3. And if there are 80 terms, then we can split that up. We can say, well, it's the sum of the first 78 terms, and then plus a79 plus a80. Now, why 78 is because that's a multiple of 3. So that's 26 times the sum of the first 3. So that's going to just be 26 times minus 3. So we're going to get minus 78. So that's 26 times minus 3 is minus 78. And then the pattern repeats again. So then plus 2 minus 4, that's the 79 in the 80th term. And if we put that all together, we get minus 80. Okay, so the next one is about a deflating balloon. And we have to show that the rate of change of the radius of the balloon is as given. And we're told that the volume of the balloon is modeled as decreasing at a constant rate. So let's write that as an equation then. So dv by dt is equal to the constant, let's just call that m, and it's decreasing. So if m is a positive 1, then we can write minus m. Now we need to link v with r. So we also know that for a spherical balloon, v is equal to 4/3 pi r cubed. So we can write down dv by dr. The derivative of that is 4 pi r squared. So dr by dt, which is what we're after, is equal to dv by dt divided by dv by dr. Because what you can if you sort of treat these derivatives like fractions, you can sort of see that the dv's would cancel out and you'd be left with dr by dt if you did that. So we're going to get minus m for dv by dt, and then divided by dv by dr, so divided by 4 pi r squared. And if we group this m over 4 pi bit together, that's just a constant, so we can see that as minus some new constant, k divided by r squared. That's the first bit done. Then we're given some boundary conditions. So we're told that the initial radius of the balloon is 40. So when t equals 0, r equals 40. After 5 seconds, the balloon has a radius of 20 centimeters. So t equals 0, r equals 20 is our next boundary condition. and the volume of the balloon continues to decrease at a constant rate until the balloon is empty. We'll need that for the last part. So let's take the equation, and this is another separable equation, so we can write this as r squared dr is equal to minus k dt. Integrate both sides, so r squared becomes r cubed over 3, and minus k just becomes minus kt plus c. So if we use our boundary conditions, so let's use this one first. The second boundary condition should be t equals 5. I don't know why I wrote 0 there. So t equals 0, r equals 40. So we got 40 cubed over 3 is equal to c. Okay, so we get that straight away. So c is equal to 64,000 over 3. We also know, if we use the second boundary condition now, so when r is equal to 20, so 20 cubed over 3 is equal to minus kt, well, t is 5, so minus 5k plus c, which we just found. So if we rearrange all of that, we get 5k is equal to 64,000 minus 20 cubed, which is 8,000 over 3. Okay, so 56,000 over 3. So k is equal to 11200 over 3. So if we put that all back together, we get r cubed over 3 minus 11200 over 3, is equal to minus 11200 over 3 times t plus 64,000 over 3. Now if we just multiply through by 3, run out of space here, we get r cubed is equal to minus 11,200 t plus 64,000. Okay, so there's our answer. We could probably have just left it as the previous line, but I think it's a little bit tidier if you multiply through by 3. So find the limitation on the values of t for which the equation in part B is valid. Well, we're told, so let's use this third bit of information now. The volume of the balloon continues to decrease at a constant rate until the balloon is empty. Okay, so when the balloon is empty, that means r is equal to 0. So r cubed, so therefore r must be positive. So r cubed must be positive. And we've got an equation for r cubed. So minus 11,200t plus 64,000 must be positive. And if we just rearrange that, so move the 64,000 over first, and then divide by minus 11,200. Remember, if you divide by a negative number, then you must change the sign of the inequality. So we get 64,000 divided by minus 11200, which simplifies to, minus sign in front of the 64,000 as well. So it simplifies to 40 over 7. So t must be less than 40 over 7 for this to be valid. If it was more than 40 over 7, then you would have some negative radius, which doesn't make sense. Okay, so next one, we've got some function that we're going to have to differentiate implicitly. So because it's a function of x and y. So implicit differentiation. With implicit differentiation, we just differentiate straight away. We don't need to rearrange for an explicit y equals f of x. So we use the product rule first of all on the left hand side. So differentiate the x squared, I get 2x, and then leave the tan y alone. Then I'm going to differentiate the tan y, but leave the x squared alone. So tan differentiates to x squared, but because it's a function of y, not x, we need to multiply by the derivative because of the chain rule. And differentiate the 9, 9's a constant, so that just differentiates to 0. So if we rearrange that, we'll move the 2x tan y to the other side, so that becomes minus 2x tan y, and then divide by the coefficient of the derivative. So x squared times x squared y. Now that looks nothing like what we're aiming for, so we need a little bit more work. So if we go back to the equation, we can say tan y is equal to 9 over x squared. Okay, so we can substitute that in, but also we know that sec squared is 1 plus tan squared. That's a Pythagorean identity, so that's going to be 1 plus 9 over x squared squared, which is 81 over x to the 4. So we're going to substitute all of that in. So I've got minus 2x times 9 over x squared, that's tan y, and then on the denominator x squared times 1 plus 81 over x to the 4. This is looking a bit more promising. I've got an 81 in there and a minus sign on top. So let's just simplify the numerator and the denominator separately first. So the numerator becomes minus 18, 2 times 9, and then x over x squared, so that's just 1 over x. And the denominator, if I just multiply the x squared through, I'm going to get x squared plus 81 over x squared. And we're almost there. All we need to then do is multiply top and bottom by x squared. So I'll get minus 18x in the numerator, and if I multiply the bottom by x squared, I get x to the 4 plus 81, which is what I'm after. Part B, prove that there's a point of inflection. Well, a point of inflection corresponds to a change in the sign of the second derivative. So that's what we're going to aim for. So we'll differentiate it again. We'll use this form of the derivative, and so we're going to have to use the quotient rule. So the quotient rule is that we differentiate the numerator first and multiply it by the denominator. Then we subtract from that the numerator times the derivative of the denominator, which is 4x cubed, and then divided by the denominator squared. Now if we simplify that, we've got minus 18x to the 4, so that's, and then we've also got minus minus plus 18x times 4x cubed, which is 72x to the 4. So 72 minus 18 is 54. So we've got 54x to the 4. And then we've got minus 18 times 81, which just using a calculator gives minus 1458. And then the numerator, we'll just leave that squared. Okay, and then all you really need to do then is just substitute in this value. So we find that that is less than 0 when x is less than the fourth root of 27. So the easiest thing to do there is just calculate the fourth root of 27 on your calculator, and then just choose a number that is a bit less than that and substitute it into the formula. If it's equal to that value, then that's equal, and if x is greater than root 4 over 27, then that's greater than 0. Okay. Okay, so we get that, and that's enough. If there's a change in sign before and after that value, a change in sign of the second derivative, then that's enough to show that there's a point of inflection at that point. Okay, on to the last question eventually. So prove by contradiction that there are no positive integers p and q such that that is true. Well, the first thing that should stand out with this equation is 4p squared minus q squared. You should, at this stage in your maths career, be able to spot difference of two squares at a distance. So 2p plus q times 2p minus q is equal to 25. Okay, so what we're going to do, prove by contradiction. So we'll assume that positive integers p and q do exist that satisfy that equation. So if they multiply together to give 25, then what we've got to think of are integers that multiply together to give 25. So 25 is equal to, we can write that as 5 times 5, or we can write that as 25 times 1. Okay, now you could also think 1 times 25, but we're going to discard that because that would mean that 2p plus q would be 1, but 2p minus q would be 25. And we know that if p and q are positive, then 2p plus q must be greater than or equal to 2p minus q. It can't be less than it. That wouldn't make sense if these are positive integers. So in the first instance, if it's 5 times 5, then we could say that 2p plus q is equal to 5. So this is 25 equals 5 times 5. So 2p plus q equals 5, or 2p plus q, 2p minus q is equal to 5. And if we solve those simultaneously, so let's just add these together, we get 4p is equal to 10, so p is equal to 2.5. Okay, the other alternative is that we wrote 25 is equal to 25 times 1. So what that means is that 2p plus q was equal to 25, and 2p minus q was equal to 1. So again, solve those simultaneously. 4p is equal to 26 when we add these, so p is equal to 6.5. And in both cases, we find that p is not an integer, so that's a contradiction. So therefore, no positive integers p and q satisfy the equation. Okay, and there we are, we finished the paper. So if you've found that useful, then please like the video and subscribe to my channel. If you're interested in any one-to-one tuition on A-level maths, A-level physics, then please visit my website, which you can find on my homepage of my channel. Okay, thanks for watching, and bye for now.